Welcome to the Explainer. Today, we're doing a technical deconstruction of Merge, specifically looking at version 0.3. Now, if you're coming from a background in object capability languages, say you're familiar with E, Joey, or Monte, or perhaps you've worked with Elixir, Erlang, or even CUDA and data flow platforms, you're going to find this pretty interesting. Merge is currently in its incubator stage, and our goal today is just informational. We're going to look at how it handles authority, execution, and parallelism. It's not about being better or worse than what you know, it's just fundamentally different.
Here is a quick look at our map for today. We'll cover the architecture, the scope and membranes, caretakers, least authority, the parallelism model, and we'll wrap up with some unique language quirks. Let's jump right in.
Section 1. Architecture and DSL context. To really understand Merg-E, you have to accept that it is humbly just a domain-specific language, or DSL, built specifically for Web 3.0 L2 nodes. It trades pure academic theory for practicality. One thing that makes it so different from a language like E is its deep symbiosis with Inuit det Voltefes. It strictly separates code namespaces from runtime namespaces. So while you'll recognize the core spirit of least authority, you'll also see some heavy influences from data flow platforms. Let's talk about the engine room. The architecture relies on a scheduler called Nidahug, and rather than a standard queue, it operates directly on Yggdrasil. Yggdrasil is essentially an in-memory, DAG-shaped database queue with 4 distinct zones. Tasks get scheduled here and are delegated out to worker event loops. And an important quirk to note right away for you systems folks, in Merg-E, locks are not semaphores. They are strictly scheduling primitives for Nidahug. The way flow control works is also quite different. Merg-E actually throws out standard flow control entirely. Things like for loops are gone, and it relies heavily on structural iterators using a primitive called an actor cedo. These are ephemeral, synchronous blocking callables, and their lifetimes are bound purely to the iterator. Moving on to Section 2, Scope, Membranes over DAGs, and the Authority Paradigm. So if you know OCAP theory, you know about caretakers and membranes, but Merg-E enforces a really stark line between them. If you are managing access to a data tree, you use a membrane. It operates over arborescent DAGs, but if you are isolating a specific function, you use a caretaker, which works over single callables. Ultimately, pruned chunks of these DAGs and DAGified callables are your prime object capability handovers. This brings us to the reserved keyword scope. In Merg-E, scope is literally a membrane over a DAG. This might include selected chunks of the lang DAG, which holds most of your language tokens, and the ambient DAG, which holds access to ambient resources. You prune that ambient DAG, and then graft or ent what you need. This is also how async argument injection works, safely pulling dependencies from resources in the ambient tree or from custom resources you define. Let's get into Section 3, Caretakers and Callables. We mentioned caretakers operate over single callables. Well, just like in classical OCAP, they act as a revocation pattern. But a unique twist here is that caretakers in Merg-E can actually double as invocation quotas. You can strictly limit the number of times a proxy function can be executed before it automatically revokes itself, which is incredibly useful in a Web 3.0 context. You also have to choose between actor and non-actor callables. Actors will persist their state and they lock their execution sequence to a single scope. Non-actors are more ephemeral. They create a brand new state per call, which means they can safely be run in parallel. Section 4 is all about least authority and isolation. Let's peel back the layers. The granularity of membranes here is something you don't typically see in Monte or Joey. You have unfreezable membranes, not top workable ones that prevent pruning entirely, non-writable membranes, RAM quota membranes, and versionable ones. A really interesting one is copy on mutate, which creates a shadow DAG for safe manipulation. All of these operate strictly under the engine's freezing and freezable rules to maintain total isolation. And because we are dealing with multi-runtime environments, memory has to be normalized. Merg-E does this using a fluid basket of goods to define what it calls RAM points. If you are grafting or nesting from the same pool, it's free. But the second you cross unrelated quota membranes, it starts consuming RAM points. All right, Section 5, let's look at parallelism and the execution model. To understand what Merg-E is, you have to understand what it explicitly lacks. It lacks traditional objects, it lacks a distributed computing model entirely, and it lacks persistent blockchain-backed VATs. Instead, it funnels all of that design energy into local-only high parallelism. So while you might feel an execution spirit similar to Erlang or Elixir, it totally abandons their distributed node setup. It behaves a lot more like a data flow framework, targeting CUDA-like parallelism. In fact, the long-term roadmap, and we're talking years away here, is to allow parallel pure compute inline lambdas to be mapped directly to cycle kernels.
Data frames here map to parallel primitives. You have to explicitly freeze the data frame, pass it to an expression, and then, because functions in Merg-E don't yield return values, only synchronization awaitables, you collect all of those awaitables in a blocker abstraction. That's how you synchronize your parallel tasks.
Finally, Section 6. Let's wrap up with some unique language quirks aimed specifically at crypto. Merg-E has strict, inert, sensitive, and mutable rules, which heavily influence explicit versus implicit capture enclosures. It also relies on argument filters, especially URI annotations, to safely route data. And on the math side, the types are massive. You have integers up to 16 kilobits, generic type math that enables overflow-free computing, large rational types, floats up to 256 bits, and complex numbers built right out of those floats.
Even the way you import code is distinct. The language gets its name from the merge keyword. It's a surgical import that wraps definitions to immediately constrain and localize authority right at the import level. And error handling avoids big, messy try-catch blocks. Merg-E uses a happy path and escape ramp approach. The error body is totally separated from your core logic, which keeps the data flow clean and predictable. So taking all this into account, the lack of traditional objects in VATs, the focus on local cycle parallelism, and relying entirely on arborescent DAGs for least authority, it forces us to look at capability models from a completely different angle. Will this pragmatic approach become the new baseline for writing Web 3.0 L2 infrastructure? It definitely gives us a lot to think about.